Okay. I started to just write down the solution, then decided, well, first place, I didn't want to do it all in my head. And in the second place, good to see the, the steps. But the steps are very straightforward, so I'm going to go through this very quickly. This equation, in the first place, let's observe that this equation is first order linear. And we're going to have to do that in a minute when m becomes a function of t. But right now m is a constant, so we can treat it as first order linear, but it's actually probably easier to do it as a separable equation. We separate it, we get this, so we integrate both sides. This is all very straightforward, but I'm going to be specific about our substitution. U is rp plus m, du then is r dp, so that dp is 1 over r du. This integral becomes then 1 over r du over u. The 1 over r is constant, it comes out in front. And then we get the natural log of u inside, which is the natural log of rp plus m. And on the right-hand side, as usual, we get t plus c. Then, of course, we're going to deal with the natural log, but first we'd better go ahead and multiply both sides by r. This constant, of course, absorbs whatever the value of r is, and it's still constant. And then we get the natural log here equals this, so that, and there are a couple of steps to this because of the absolute value sign and so forth, but it turns out that rp plus m is going to be ae to the rt, and I should have indicated up here as well that a is not equal to 0. Of course, if a equals 0, you have no change. And yeah, it's a trivial case. But, okay, then we solve this for p. And the way I solve for p is I first divided both sides by little r. The a divided by little r absorbs the constant, right? So we have this, and then we just subtract m over r from both sides. And I observed, and you should maybe work out the details of why, if we know the population at time 0, the p of 0, then a has to be p of 0 plus m over r. And your population would then be p of 0 plus m over r e to the rt minus m over r. Okay? Now, given your conditions, you would have to interpret it. You might not be given the population at t equals 0. You might be given the population at a later time. You could still figure this out if you're given sufficient information. Okay, so that one is a pretty straightforward situation, but it's a bridge to the more general situation. For example, if you're talking about a population, you could have a cyclical population. You know, if the seasons influence the migration rate, then t would tend to be a periodic function, a period of 1 year. And the nature of that function, well, it can get pretty complicated, but we're just going to assume one where the migration rate is just some sine or cosine function with a period of 1 year.